if you're here, please start the recording.
Already done.
Okay, perfect. Thank you. So I guess you can see my desktop. Today is Thursday, so this is our timeline for today. So we're gonna see something about quantum computing with neutral atoms. Basically, Sinega is collaborated with a French startup that is Pascal, and they are using neutral atoms trapped inside the chamber, and they use pulses to perform quantum computation. So it's something a little bit more at the lower level, which means at the hardware level. So a way of performing quantum computation at more hardware level than what we have seen before with a gate model. Okay, and this kind of device so allow for something that is called analog quantum computation. Then we will see we'll explain more in detail what are NISQ devices and which kind of algorithm they can run, or scientists believe that are good for this kind of devices. Then in the afternoon, we will have a lecture about quantum communication and cryptography. Okay. Okay. So in the homepage of the course, you can find the two slides, the two presentations that we have today, and also the hands-on, the Jupyter notebook for the practical session, okay, as well as on the GitLab. Okay, so yeah, let's start. So yeah, welcome to this day 4. As I said, we're going to see neutral atoms, quantum computation, and later on, what are these NISQ devices and how can we use them? So this is basically the content that we have, the agenda that we have today. So as first, we will have an intro and a recap of what you have seen about the hardware and the ecosystem. Then we will go deeper into the hardware of a neutral atom quantum computer. Then we will have a programming session where I'm going to show you how to program this quantum computer with neutral atoms in an analog way. And there is this software that is called Pulsar. This is like Qiskit, but for neutral atoms quantum computation. And later we have the algorithm for NISQ devices, and then we also have an application using Pulsar, a QA application. So this quantum algorithm for NISQ device, this is called QAOA, is for optimization, and we're gonna apply this using Pulsar to a problem that is the maximum independent set problem. Okay, we are also gonna have a lecture from 12 to half past 12. This lecture is gonna be it is gonna be a talk by Professor Leonardo Guidoni about another algorithm that is NISQ algorithm that is called VQE, that is for variational quantum eigensolver, that is used for molecular simulations. Okay, so the last 30 minutes we will have this talk by an expert of the field. Okay, so okay, let's start with the first part. So we have seen that there exists this different qubit, physical realization of qubits in the that constitute the basis of your quantum computing hardware. We have superconducting, like the one employed by Google, or maybe I also have the we have the superconducting. Superconducting means you are using a superconducting circuit that has to be cooled down to very low temperature, very close to the absolute zero, and they show like superposition in the current that circulates in these circuits. Okay, so that's how you construct your qubit, and this is the technology that is the most advanced, let's say, or basically is the technology that we know better how to use. And this is the technology used by IBM for their computer, by Google also, by another company in US or Canada, I think US, is called Rigetti. And also the Wave that we have seen yesterday, they use superconducting circuit but for quantum annealing. Okay, let's go down. We have photonic devices. So if you read the news, some time ago, some Chinese university proved quantum supremacy using a photonic device. In 2018, Google proved quantum supremacy for, let's say, random sampling on their computer. Chinese people use photonic devices to show quantum advantage in something that is called boson sampling. However, there is also a startup that is called Xanadu, which is a US company which uses this kind of technology. Okay, so basically you encode the state of a qubit into something that is called a squeeze state of light. So you use photons, a particular state of photons that show entanglement, that show so qubits are in a superposition in this squeeze state. Then they go through waveguides and they interact with one each other, the photons, in order to perform a computation. And at the end, you have the measurement. We have topological quantum computers. Okay, these are a little bit more far-fetched, probably, because the nice thing about topological is that quantum computation is encoded into the topology of what you're doing. So it's so error protection comes natural with the fact that you're encoding into the topology, because as you know, topology doesn't change if you disturb the system locally, let's say. And that's what Microsoft is doing, but right now we need major advances in like understanding, okay, the basics concept of topological quantum computation, okay, in order to be able to build this kind of devices. We have diamond center, so they use diamonds, vacancies in the diamonds to create the state of a qubit. And there is this Australian company, Quantum Brilliance, that is working with this technology. We also have IonQ. IonQ, also a US company, which uses trapped ions. So you have ions. So qubits are encoded into the electronic level. So you have microscopic qubits are microscopic object in this case, and you trap them using electromagnetic fields, or trapped for ions, and you can work with them. You can make them interact and create gates using lasers, laser pulses. So that's IonQ. And finally, we have what we are gonna discuss today. Sorry, this was not in presentation mode. Okay, now it's presentation mode. So, and we have Pascal. So as I told you, Pascal is this French startup, and they're working with neutral atoms. So the technology is quite similar to trapped ions, but with neutral ones. So yeah, basically they have this vapor of atoms that they are able to trap into a vacuum chamber, and then using pulses, they interact with the atoms and make them compute. Okay, so qubit is encoded in the electronic level of the neutral atoms. Okay, why am I focusing, let's say, so much on this device? And not only because it's one of the few European technology, but also because Pascal has been chosen by this project. It is called Pilot on Quantum Simulator. So it's an Euro HPC project. And this project will last for years. And the aim is to create the conditions to integrate quantum simulators. I mean, simulators, I'm going to call quantum device of Pascal, since it is an analog quantum computer. We will also call it a quantum simulator. Okay, so the aim is to create this integrated ecosystem, and so integrate Pascal device with HPC HPC systems that are spread around Europe. Okay, and Pascal, what they have is a quantum computer prototype, so able to perform analog computation. That's why we call it quantum simulator, with 100 qubits, and they plan to be able to scale it up to 1,000 qubit in a few years. Okay, couple of years probably. Okay, so let me show you, okay, what is the stack, what is the quantum stack of, so what are the levels of I mean, what are the different levels of this quantum stack, okay, of that this project about this pilot on quantum simulator proposes. Okay, so at the lowest level we have the quantum hardware. So in this case, in the case of this project, is going to be the Pascal hardware. So it's going to be something about quantum registers. So we have atoms inside this vacuum chamber, and laser controls to manipulate the state of the system, and also to trap the system inside this vacuum chamber. And we also have detection to measure, okay, the qubits. Okay, and this is going to be the hardware part. The upper level, so, is the quantum software. Okay, quantum software can be of two kinds. Okay, as I told you, there is a lower level way of programming, which is exactly programming the lasers. Okay, so, and that's analog programming, which means you modify the laser pulses that control your system, and in order to modify their Hamiltonian, so the function that is associated with the energy, okay, with the evolution of your quantum system. Okay, and you can perform computation in this analog way by just looking at the lasers. Okay, then there will be in the future also a higher level way of programming, which means like Qiskit, no? You're gonna define a sequence of gates, okay? And in the Pascal device, you will be able to program the quantum computer via Cirq. Cirq basically is the equivalent of Qiskit that we've seen yesterday, but we've seen the second day. But Cirq is developed by Google. Okay, so what digital control means is that the programmer, basically chooses the gates. Then the gates, of course, are mapped to a correct sequence of pulses, and then they are sent to the hardware. Okay, so there is these two levels. Okay, pulsar is more hardware level. Cirq, like Qiskit, is more it's a more higher level, let's say. Okay, but anyway, you have to always go through the you always have to use pulsar at some point, no? Because pulsar is the one that encodes what you want to do into a sequence of pulses or laser pulses. Okay. Then what we have is the last part of the quantum stack is the level of the applications. Okay, so what does it mean, application, for this kind of device? That you can try to run on it, since the hardware is limited in size, so it has 100 up to 1000 qubits. So you cannot run, for example, as we have seen yesterday, Shor algorithm, for example, that require error correction and thousands or hundreds of thousands of qubits. So what you can run are NISQ algorithms, or NISQ-ready algorithms, where NISQ stands for Noisy Intermediate Scale Quantum Computer. So noisy, there's no error correction, there are noise. Intermediate scale, because they're not large scale, they cannot run Shor algorithm or Grover search. And quantum, of course, because they're quantum device. And this kind of application that this NISQ algorithm can solve are probably very still interesting, because this NISQ algorithm can be used for quantum simulation, like in chemistry, in drug discovery, but also in problem like optimization and machine learning. Okay, so this kind of algorithm, so there are, let's say, three major classes belonging to the NISQ algorithm set, and one of this class is one element of this class is VQE, which is variational quantum eigensolver, which is used to calculate the ground state of molecules. Then we have QAOA, which stands for quantum approximate optimization algorithm. It's something like similar to what the wave, so with quantum annealing, is doing, but on a gate model, okay, or a quantum device, right? So the objective here is to solve an optimization problem, which is expressed as an easing problem or a cube problem. Okay, it's similar to what we've seen yesterday, but in the context of gate models, quantum devices. Then we have the part of quantum neural network, and that we are gonna see more in detail tomorrow. Okay, and also here you have different proposal to realize something that is similar to what neural network do, but on a quantum computer. Okay, here, okay, you can see an example of a convolution neural network. So each line is a qubit. Then you perform operations and measurement in order to reduce the dimensionality. And at the end, you try to classify the initial image that you have to encode at the beginning using probably this U1 gate. Okay. So, okay, what's the nice part of this algorithm is that most of them are hybrid algorithms. So they run part of the algorithm on the quantum computer and another part on a classical computer. So that's why HPC is also important, okay, to work together. And so it's not only quantum computer alone that can provide some speed up or some increase in the quality of the solution. It's the combination of classical computer and quantum computer together working to improve the classical solution alone. Okay. Okay, so what we are gonna see now is the quantum hardware part. And yeah, we're gonna introduce the Pascal quantum hardware. Okay. So this was a little bit an introduction. So basically it's an overview of what we are going to see next in the rest of the day, but more in detail. Okay. Okay, so let's start with Pascal. So with quantum computing with neutral atoms. So Pascal, the quantum computer made by Pascal employs rubidium atoms. So the neutral atoms that they choose are rubidium. This because they have particular properties that we're gonna see during the next slides. Okay. So rubidium atom is an atom that has basically one electron in the last orbital. Okay, in the outside orbital. Okay. So, okay, how do they construct their QPU? So they use these rubidium atoms, but then the state of a qubit. So state, the basis for the state of a qubit is 0, 1. So the 0, 1 state are encoded into 2 electronic levels of the rubidium atom. So we're gonna call G and R. So as you can see on the left, okay, the rubidium atom has many electronic levels, and they're able to choose from the beginning exactly 2 levels. Okay, so G stands for ground, and R is an excited state. So basically, your atom starts in the ground. Then, if you give him some energy, if you shine some photon, which means some laser, you're gonna acquire some energy and stay in the R state, which is the 1 qubit state. Okay. What's the nice thing about using atoms, so that it is microscopical to use to encode the state of your qubit. You have this nice thing about nature that is the following. So atoms of the same element, okay, are indistinguishable. Okay, so if the qubits are encoded into the same energy levels, then they are strictly identical by nature. Okay, so you don't have, like maybe in superconducting circuits, you have some defects due to the fabrication of this macroscopic device at the end. Here, instead, for sure, it's harder to manipulate something that is so small as like an atom, but then you have qubits that are identical. Okay, that you can treat as identical. Okay, this is a great advantage. Okay? By looking into the future, now it's going to be a great advantage when this technology will be more mature in the next years, okay? Because it will, thanks to this fact, we will have low error levels, okay? And you perform your quantum computation, okay? Due to this fact. Okay. There is one question. Can you give me the scramble from it? Okay, that's something that we are going to see about. What we're going to see next, what I mean between a hybrid algorithm that run on quantum and classic. Okay? We're going to see it later on. Okay. So I don't want to spoil anything. Okay, so as I told you, G and R are called, so ground is the ground state, R is the read bear state. And what are other properties of these two states inside the rubidium atoms? So they have a long decay time. So as I told you before, you can start from G, shine some light, some photon, or so on laser. They use are lasers, and they can excite the state G into R, and the atom tends to stay for quite a long time, okay, into this state R. So you don't immediately go back to the ground state. So they have long decay time. So they can stay in the R state for quite enough time to perform computation. And then there is some strong interaction between atoms, which means that in order, if you want to perform quantum computation, you have to enable entanglement, okay, between atoms, and so superposition of multiple atoms, or multiple qubits, and you can do that making the atoms interact one each other. Okay, they have strong interaction because in Rydberg state they have. Let's say they're using electrons that are very far from they are in an orbital that are very far, so that's why they can interact strongly. Okay, so let's go on and okay, let's start to understand how the experimental setup, how the quantum computer is so what's the structure, experimental setup of this quantum computer. So they have a vacuum chamber, so where you release the atomic vapor, so the atoms are the rubidium atoms, and I mean, inside this vacuum chamber there should be only the rubidium atoms. Okay, you don't want other particle, other atoms. So you have to produce an ultra high vacuum state inside this chamber here. Then another nice thing about rubidium atoms is that they are in a vapor state, so liquid vapor state at room temperature. So you don't have to cool everything down like in the to the absolute zero, like in superconducting or other technologies. Here you can stay at room temperature. Okay? You only have to, I mean, you still have to produce a ultra high vacuum, okay? But they can definitely work at room temperature. Okay, yeah, we're going to also see this one in the next few slides. Okay. So interaction is, however, interaction between qubits is done. Everything is done with pulses, with the lasers. Okay, lasers change the Hamiltonian, so change the energy and the evolution, change the energy of the system, and also define how the evolution of the system so basically, laser change the Hamiltonian. Okay, Hamiltonian is the function that represents the energy, but also describes the evolution of the system. Okay, so laser change the Hamiltonian. That's how they allow interaction between qubits and single qubit operations. Okay, but we're gonna see it later. So what happens also? How do they trap these neutral atoms? So what they use are something that is called optical tweezers. So it's like this purple beam, okay, that then goes inside. The optical tweezers are particular laser beams that are controlled by these devices. This is a 2D AOD, okay, but okay, doesn't matter. And they also have other laser beam that also allow help to control to trap atoms. So basically, the tweezer are lasers, okay, and due to some physical concept, they are able to trap atoms in the center of the laser, let's say. So the laser has the intensity of the laser is something like a Gaussian. So if an atom is shining with this laser, there are some forces that push the atom inside the peak of this Gaussian beam. Okay, so that's what optical tweezer, let's say briefly, the working principle of an optical tweezers. And the nice thing is that, I mean, you can move them, and each tweezer traps a single atom. Okay, so by moving the tweezers, so by operating the tweezer, you can also move the atoms inside the chamber. So what does it mean? It means you can move your qubits, okay, and you can basically create the topology that you want. Okay, so in fact, okay, that's what I'm going to show you here. Yeah, so by moving the optical tweezer, it's possible to arrange the topology of the qubits or the rubidium atoms. Okay, so that's because a single tweezer control a single atom. Okay, so right now I think they are able to do it on a 2D. So all the atoms are in the same plane, and they move them in the same plane. So yeah, that's it. And you can arrange them in every way you want in 2D right now. But they're also working on expanding the topology to 3D. So something like this. This is going to be available probably in a couple of years in Pascal devices. And as you understand, okay, this is also a nice thing about quantum computers, quantum hardwares that use atoms, okay, because you can move them and make them interact in the way you want. So you can arrange different topologies. Okay, that's not what happens for superconducting circuits, where you have a fixed topology. So you know, because they are printed circuit. Okay, you know that this qubit only interacts with the neighbors, and it's gonna be so you cannot change the topology there. Okay, you have to choose the topology from the beginning. And that could be an advantage for neutral atoms quantum computation, because is it possible via optical tweezer? So with this optical tweezer, you can I think you can just like move the tweezer, so relocate the beam that you're shining. So move the beam, and then the atom will remain in the center of the beam. So, and then you can move the atom. So something like this. Okay. Just move the tweezer. Okay. Just move the laser. Okay, and then yeah, exactly. So yeah, exactly. Okay, how you assure that there is only one rubidium atom? I don't know that. I know that. So laser. So these tweezers are very small, no? So let's say the cross section, okay, of this laser is so small that, and by default that let's say it can trap only one atom. Okay, two atoms cannot be trapped because there's no space. Okay, so because the cross section of the laser is small. Okay, probably is that the yeah exactly. Yeah, exactly. Okay, let's go on. Yeah, okay, so you know which is the size of the atom, and you're not shining something that is huge, you're shining something that is basically of the same, more or less of the same dimension of the atom, maybe. Okay. Okay, so let's go on. So, okay, so we understood that Pascal devices have so encode qubits into electronic structure in the ground and the Rydberg state. We have this vacuum chamber, optical twists that can arrange them in different topologies, but how quantum computation is performed. Okay, again, they use pulses, so lasers, which could be local lasers, so acting on single qubits or single atoms, or global pulses that operate on ensemble or on all atom or ensemble of them. And with these pulses, you can both produce something like the X gate. Okay, you can excite a qubit, so to the one state, but you can also perform something that's like C0. Okay, so you can perform computation in this way. So in general, every gate that we've seen yesterday, control gate, zeta gate, sorry, X gate, zeta gate, control gate, they are a specific combination of global and local pulses. Okay. Okay, let's see now. Okay, let's see now. So how you can. So there is one principle that they use to create entanglement. Okay. It is called the Rydberg blockade. Okay, Rydberg blockade. What does it mean? It means that qubits that are within some range, the range of the Rydberg blockade, can interact each other. Okay, so so if you can see the plot on the left, okay, the Rydberg blockade is here in the middle. Okay, if let's say they are far, so they are not within the Rydberg blockade radius, okay? If you shine, okay, some light, okay, if you excite them with the global pulse, you so the transition that you have is from the ground to the 1-1 state, so still classical state, okay? But if they are inside the Rydberg radius, okay, inside the Rydberg radius, the interaction is so strong that the state RR becomes inaccessible, okay? So if you excite them with the global pulse, for example, you the resulting state, since the energy of the Rydberg state is so high that you cannot reach it, the final state, the state that you obtain is something that looks like this. So it's something like, it's an entangled state, okay? It's what we called yesterday, so it's a Bell pair, no? Okay? It's something that you would obtain in a gate model quantum computer with an Hadamard gate on one qubit and a control knot on the other, right? So if you remember what we did yesterday, with an Hadamard gate, you put one of the two qubits into 0 plus 1, and then with the control knot, you put also the other in the same state, okay? So you obtain this kind of Bell state, okay? Maybe you need to at first to put a bit flip here, X, and then you get exactly this one here, okay? Okay, so that's why you obtain something that is with the so the blockade radius, the Rydberg blockade radius is very important because so it's this distance within, and if atoms are within this distance, they can interact in a way that is not classical. So you can find them in a quantum state that is a superposition state, okay? And you get something that is similar to having control knot. So, I mean, this Hadamard and then control knot, okay? Then I guess you need a 2D profile for the tweezer and control laser. That's minus the Rydberg blockade. Ah, okay. You mean for the tweezer? Yeah, probably yes. Yeah. You mean in order not to overlap too much the tweezers? Okay, something like that. Yeah, probably yes. Okay. So let me go on. So okay, mathematically, then maybe things get more clear. Okay, how these lasers interact with the qubits? Okay, how they can modify the state of qubits. That's because lasers, okay, when they interact with qubit, they modify the Hamiltonian. So the function that describes the energy of the atoms of the qubit system, and also the same function is the one that governs the evolution in the system. You know that we have seen before that this kind of quantum system evolves via a Schrödinger equation in time. So a Schrödinger equation, the one that determines, let's say, how the Schrödinger equation is done, is exactly the Hamiltonian. Okay, so yeah, okay, and I don't know if okay, yeah. And if you can see here, we have different terms. Okay, these terms depend on different parameters. So we have omega, delta, and u. And these three parameters depend exactly on on how the laser that interacts with the qubit register is done. Okay, on how on which kind of laser are you, which are the properties, let's say, of the laser. Okay, fact. Okay, here probably everything is going to be clear. Okay, you have so you shine your laser, and laser has something. So you select the intensity of your laser and the frequency. I mean, yeah, and the tuning of your laser. Okay, so here you have how the laser interact with the qubits. Okay, you have this term. This is called the Rabi frequency. That is proportional to the intensity, to the amplitude. Okay, yeah, here of the laser that operates on the qubit. Then we have the detuning. So that is yeah, defining. Here you have here an example of pulse. Okay, so these two, Rabi frequency and detuning, are controlled by changing intensity and frequency of the laser. Okay, so basically, yeah, as I told you, the Rabi frequency is proportional to the intensity, and the detuning is basically the difference between the frequency that separate the ground state from the R state. So the frequency, the atomic frequency of the transition between ground and readback, and the frequency of the laser. So it's basically the difference between the two. Okay. What about this third term? Okay, the third term is C that is a constant over the distance between qubit I and qubit J. So by varying the topology, so this term varies with the topology. Okay, arranging them in different way, you can reach, you can have different, let's say, interaction between them. So I want to show you this thing. Okay, so the Rabi frequency modulates this term that is a sigma x, that is something like an X gate. The detuning modulates this term that is a phase gate, so something like Z, like zeta. And these two terms, so Ni or Nj, where Nj is defined in this way, so they basically give you the interaction term. So the how the it's the interaction term between qubits. Okay, so basically probably now it's more clear how laser operate or change the state of the system. Okay, because they change the Hamiltonian, which change the state again. Okay, because the Hamiltonian is responsible for state change. Okay. Okay, let's go on. Okay. The final part of like in every quantum device is the measurement. So basically, they also have other lasers that are shined on the qubit register, and they observe the fluorescent image coming out. So they have this camera that is able to check, okay, the image coming from the fluorescence of this of the atoms. Okay, and usually I mean, what they have in this device is that at the end, as you know, the measurement is classical. Okay, so either you get a 0, so a ground, or read back. So either get 0 or a 1. Okay, so basically in this final image of fluorescence, they get that qubit in the 0 state appear bright, while the qubit in the 1 are dark. Okay, so that's how they check, okay, the final state, they measure the final state. Okay. Okay, are there questions concerning this part before we go on to the second level of the quantum stack, the software? I guess I more or less answered to the question that you had so far. Do you have other? Oh, okay. Sigma. Oh, sorry. You mean this? Yeah. Okay. This delta. Ah. Okay. Sigma. Okay. Sigma. Sigma is sigma is exactly the sigma xi, sigma zi are the Pauli matrices. Yeah. So sigma x, it's like the bit flip. So it's 0, 1, 1, 0. Sigma z is 1, 0, 0, minus 1. Okay. Yeah, exactly that. Yeah. Okay, if okay, the entanglement. Okay, is this is called the block radius. Okay. Here, you just maybe look at this plot. Okay. Here on the x-axis there is the distance between the two atoms. Here you have in the middle the Rydberg blockade, and here you have the energy of the different levels. Okay, you have the ground that has some low energy, and there is the disentangle, the energy associated to this entangled state. Then you have this Rydberg energy. Okay, when you okay, if the two atoms are in the ground state and they are far, and you shine some laser, so you excitate them, what you obtain is that you obtain a transition from the ground to the RR state. Okay, that's when the two atoms are far from each other. Okay. Okay, if they are far, so which means they do not interact, and you shine a laser on them, they get excited, but they get excited in a classical way. Okay. Yeah. Okay. When the two atoms are close, okay, so they cross the Rydberg blockade. Okay. What happens is that the energy associated to the state where both atoms are excited and close gets an increase in energy. Like, yeah, as, yeah. So which means that, why? Because, yeah, as yeah, Lucius said, yeah, they are very close, and the excited atoms are very far from the nucleus, because this is the property of these Rydberg atoms. Okay, and two electrons that are very close feel something like a repulsive force. Okay, so that's why, very briefly, the energy increase a lot. Okay, so if you shine light, the the transition to this state, RR, becomes inaccessible because you don't have enough energy to reach this state here. So you are, if you shine, you are left in an intermediate state that is an entangled state. Okay. So that's the okay, basically the idea. Okay, so yeah, this is the way you create entanglement. Okay. Okay, you can move them using the optical tweezers. So you can arrange the topology you want. So you can place them using the tweezer. So you have basically the tweezer are different lasers that govern the position of the atoms, and so you can simply move the tweezer, and so by consequence also the atoms or the qubit will get closer. Okay. You know from the beginning the exact position of all the atoms. Okay. But maybe okay, this is something that will be even more clear with the practice session, because we're gonna have a look at pulsar, so how you control this quantum device. Okay, so as I told you, pulsar is this lower level of programming. Lower level doesn't mean it's not well done, but it's more close to the hardware. Okay, with pulsar you manipulate the Hamiltonian using laser pulses that vary this term, and this term. Okay, so this is varied with intensity. This is varied with the frequency of the laser, and this is varied with the position of the tweezer, basically with the topology. Okay. Later on, okay, in the future, okay, it's not that it's available right now, but you will use no more pulsar for this analog way of performing quantum computation, but circ, which is something like QC that works with gates for this digital processing, so which means using gates. But each gate again is a combination of pulses, of course. Okay. Okay, so what is Pulsar? Pulsar is this Python software library for programming the Pascal devices at the laser pulse level. Okay, and basically you can design a pulse sequence that represent the parameters omega, delta, and u of the computation. Then the sequence is read and executed by the QPU, so the real hardware, or you can do your emulation, okay, on a classical machine, okay, simulation or emulation. I mean, so this is the scheme. Yeah, you have different channels. There are local or global channels. So local that have a specific target. Okay, you define your pulses, you have your register, and then you send this sequence of pulses here to the real QPU or to a classical simulator, okay, or emulator. Okay, that's now it's time for the practice session. Let's see. Okay, yeah, probably. Where this amount? Yeah, probably, yeah. Okay, so we're gonna have this practice session where we're gonna define pulses, and we're gonna see in Pulsar how this is done, how you can define local and global pulses, and yeah. So if you didn't do that, you can go to this GitHub here, and they have so in GitHub they have the code for Pulsar, and then you can install via pip install Pulsar on your local machine, or use the forward to. So now, okay, now I'm gonna show you on my device. You can also download the examples that we're gonna see here from here. Okay. So okay, let's go.
Sorry, Ricardo.
Yeah.
Do we actually need to clone the GitHub repo to be able to run the IPython notebook? I suppose we do.
Right. If you're doing it locally,
yes.
Well, actually, I don't remember. Not sure.
Okay, I'll try.
Yeah. Or just pip install Pulsar probably is enough. I really don't remember right now. Okay. However, if you're using forward 2, it's already installed. Okay. Then, okay, let's see how Pulsar works. Okay, on it's again Python, and I'm gonna show you. I'm gonna run together with you this code. Okay, the first example that you're gonna see is about creating a pulse sequence. Okay, so I import everything I need in Python. Okay, first of all, let's create a register of qubits. So what the register does is to define the position and the name of the atoms. So you can also customize it in different ways. Okay, let's now see what this part of the code does. So here what I want to do is to place the qubit on a square lattice. So I want L qubits on each side of this square lattice. So I put L equal 5. So here this one creates basically an array, an array of positions. Okay. Let me comment this one because we're gonna see it later. This here, so here it's how you define the register. You call the register qubits, where the qubits are a dictionary that takes in input an enumeration of this square. Okay, so what you get. Okay, let's show this one. Okay, let's copy register register into register 1. But what I want to show you is how you can draw. So you can draw the register in this way. So each one of these is a qubit. Each one is labeled with a number. Okay. Then you can modify the position of the qubits. You can, for example, displace around the mean. So what you get is this one. Now 0 is in the center. And then you can also spread them, so increase the size of the lattice by 5 times, so you get something that is more spaced, okay? That has a better spacing, okay? So that's your register of qubits. Then what we're gonna do is you can also rotate, for example, the qubit register. So the meaning of this is that you can create basically the topology that you need. Okay, you can this positioning of the atoms is done with the tweezers. Okay, the tweezer are able to, of course, if you they have some interval, so you cannot put two qubits one over the other. Okay, they should be distant at least I don't remember five micro. Don't remember exactly 5 micrometers. I think this, but I'm not sure. Okay, so but of course, if you try to place them too close, there's going to be an error at some point. Okay, you can also, okay, that's the standard way of creating a register. You can also create using the from coordinate method. Let's see what it does. And okay, you can also tell a prefix in order to change the label, but okay, that's not much very important. Now let's do something that is more complex. Okay, here let's try at first 10, or let's see what happens. So here we place the atoms in a ring. The distance between atoms is defined, yeah, by this part of the code. Then you create the register, yeah, and you have something that looks like this. Probably the distance is 5 micrometers. Yeah, because yeah, okay, because the interatomic distance is 10, so probably is half. Okay, so here we have, so you can increase the number of atoms like 25, and you get more atoms. Okay, what happens if I get 50? Okay, you can also have 50. So it depends on the yeah, but at this point you can do almost everything. Then on the real hardware or on the emulator of the real hardware, you will have some constraint. Okay, so let's leave it 25. Okay, you can also do something more exotic. So you can also consider the this file of coordinates and place them in accordance with the coordinates in this file. So the file name, okay, this is a question for you. This is not a question, it's more of a joke. So the question is called ML cohorts. So remember that the startup, so the Pascal company is a French company. So what do you think is going to happen here below? So what's the shape of the next if I run this one? Okay, the interatomic distance, I'm not sure. I don't remember exactly. I suspect a few micrometers, 5 micrometers. Since I've written here, probably it's something that is also real, but I'm not sure. So, but yeah, I can then find. Yeah, I'm not sure exactly. Yeah, not sure, but I can check later on during the break. Okay, what is the minimum the minimum distance that you can have? Okay, So yeah, okay, let's try this this stupid thing. So write in the chat, what do you think is gonna be the next shape? Okay, if I run this code, what do you expect? Remember that this is called ML, and the Pascal is a French company. So if I run this, which graph? Okay, if some of you want to do this game, otherwise I'm gonna. Please write in the chat, what do you think is ML? What do you think ML stands for? If you have no idea, write no idea. And remember that you can arrange arms into D in almost every way you want. Okay, something that didn't cheat. So ML, it stands for yeah, right, exactly. Yeah, it's the Mona Lisa. Yeah, so yeah, which is hardly French, by the way. Yeah, right, exactly. That is also true. Yeah. Okay, at least I can use the Mona Lisa coordinate to break the French, the Pascal hardware. Okay, probably. So probably it's not useful to set your qubit register as the Mona Lisa, or maybe yes, I don't know. Maybe Leonardo da Vinci was so smart to also see that it's going to be useful for quantum, but I don't think so. So okay, but this just to show you that you can basically, as far as you are in the 2D, you can do almost everything. Okay, as far as you are in the you respect the distance between the minimum distance between atoms. Okay, but okay, maybe we can see. Okay. So okay, let's start with the sequence. Okay. So this part initializes the sequence. So we have this sequence command, and we will import this device, which is Chadok or Shadow, I don't know, which reflects the real device, or you can also import a mock device from yeah, this is just a device. So if you draw your sequence, okay, let's try something. So this is Chadok 2 is like as the property of the same of the real device. So let's see if I put here 1, so my register is now shrinked. So what happens if I give this register to, okay, still no error. Okay, let's see. Okay, I shrink everything between -2 and 2 micrometers, and then it says that qubit positioning don't respect the minimal distance. Okay, so probably let's go with 2. So it could be, yeah, again, it could be 5. I guess 5 is the 5 micrometers is the minimum distance, I guess, because yeah, as you can see here, since CHAdOC2 is the real device, and they say, yeah, with 5 you don't have the error, so probably that's the minimum distance. Okay, however, and you can initiate the sequence with this sequence function that takes in input your register and your device. But you can also create a mock device that has, I don't know, it has minimum distance one micrometer, for example. Okay, but then it's not sure that it's going to be physically realizable. Okay. Okay, let's. Okay, we did this. Okay, then let's declare the channels. So the laser that we want to use. So we can have different channels. We have, as we have seen, we have a global channel and 2 local channels. And this tells you the maximum of the tuning, the maximum amplitude that you can have. The basis, of course, is ground Rydberg, so G and R. And local ones also have a target, because you have to target them into a specific atom. And they have also this nice thing is target time. So they need 100 nanoseconds to find the atom. Okay. So for example, if Rydberg local was at first acting on qubit 1, and then you say, no, Rydberg local, don't act on qubit 1 no more, but control qubit 4. So the laser need 100 nanoseconds to find qubit 4 and operate on it. Okay, that's the meaning of target time. And yeah, you can have also local are of 2 kinds, one Rydberg and one is Raman. So, but I'm not gonna. So yeah, Rydberg basically, if I'm not wrong, allow transition between ground Rydberg and between ground and Rydberg. Raman also allow transition to a different levels that is called an hyperfine level that is not ground, is not Rydberg, and it's maybe useful in some cases. Okay. So again, you can declare the channel that I want to use. So I say that channel 0 is going to be Rydberg global. No, sorry. The available channels are all 3 at the beginning. So then I want channel 0 to be Raman local. I want channel 1 to be a Rydberg local, and I want channel 2 to be a Rydberg global. Okay. So, and here it tells you which are the available channel after you declared one. Okay. But anytime you can check. Okay, if you're not sure what you did, you can check. So channel 0 is local, channel 1 again is local, channel 2 is global. Okay. Then you can compose a sequence. So, okay, one thing that I did here, for example, okay, when I declare the channel, I declare this local channel 0 without specifying the target. While channel 1, I specify the target in the initialization of the channel. Okay, so this is target 4. This has no target, but then I have to add the target, and the target is qubit 1 for channel 0. Okay, that's the meaning. And then now I'm gonna create a simple pulse. So this simple pulse is a constant pulse with 2 okay, the first one is the time, last 200 nanoseconds. The amplitude is, so the Rabi frequency is 2 megahertz, the detuning is minus 10 megahertz, and there is no phase. And you can, and I add it to the channel 0. And we want to deactivate channel 1 for 100 nanosecond. And but okay, and that's our constant pulse. Okay, and that's how you declare it. But now, if I want something that is more complicated, I use these two functions that are already built, that are called Blackman waveform and ramp waveform. One is for the amplitude, one for the detuning. Okay, instead of describing the properties, I'm going to show you what are these two. So the amplitude is going to be this, something like this, and the detuning is going to be something like this. So you can also, if you want, you can also you find the integral. Could be useful in some cases, because if you increase, so here you specify basically the area below this waveform. So this means that if you decrease the time, it's going to be much more peaked because the area is constant. And okay, so sometimes it could be useful. So then what I want to do is to draw. Okay, this is again the drawing of my pulse. So as this amplitude, so this Rabi frequency is associated to this amplitude, and this is the tuning. And we can add it to channel 1. Oh, now we can do the print sequence to see what's going on. So basically what I do is, what I've done so far is the following. So I have channel 0, whose initial target is 1, and in channel 0, from time 0 to time 200 nanosecond, I apply this pulse here. This is a constant pulse. While for channel 1, I delay it, so I is inactive for the first 100 nanoseconds. The target is 4, qubit 4. Then from 100 to for 1,000 nanosecond, applies this waveform, that complex waveform that I've defined, and nothing happens on the global channel. Okay, so I can also draw everything to make it more clear. And so if I draw, everything looks like this. Okay, so I define my two pulses. Okay. Okay, right. Okay. Let's now see how pulsar handles. So the sequence handles conflict. So for example, what I do is add the same channel. I mean, channel 1, channel 0. I added. I retargeted channel 0 to qubit 4, and then I apply the same complex pulse using channel 0 on qubit 4. So since qubit 4 is already shined by the laser from channel 1, what pulsar does here is to wait until the first sequence is complete. This sequence applied to qubit 4. So the qubit is in this yellow orange square. Okay, so the standard way is to wait for the pulses for the previous pulse on the same qubit to finish, and then you apply the other one. But you can also you have also different protocols that allow you to to do something else. So for example, here on what you do is you channel one you retarget it to qubit 0, and then you apply the simple pulse with this that is called minimum delay, so you don't wait anything here. So you just need the 100 nanosecond to find the target, and then you apply this pulse to qubit 0. But then you also have this other one, this wait for all, which even though it's on qubit 0, waits wait until the qubit 4 has finished its wait until channel 0 has finished it's finished to apply the laser to qubit 4. Okay, even though it's on another qubit. Okay, so then we also have no delay, if I'm not wrong. Okay, no delay is the last thing that so both channel 0 and channel 1 operate on qubit 0, and with no delay they shine at the same time a pulse on the qubit 0. So you can have all these different combination of your sequences. Finally, you have, of course, the measurement, and the measurement you okay, of course, the base is going to be ground and Rydberg. And yeah, in the sequence, when you draw the base, when you draw the measurement, is something like this. Okay, at the end you measure. Okay, you have to define the measurement. Okay, and yes, I guess we can stop right now. We can stop here. So what you've seen is so the quantum software. Okay, now what we're going to see after the break is the quantum algorithm of NISQ devices, I think. Okay, so yeah, do you have questions concerning this first part, the hardware and software part, before going to the application part? If you have, please write in the chat or use your microphone. And if not, let's have a 15-minute break. And see you at, let's say, 10:50. So, yeah. So if you don't have questions concerning this part, please, so see you at 10:50. 10:50, 53, 50, 52, okay. 15-minute break. But if you have questions, please, I'm here and write in the chat. So, okay, so there are no questions. So let's see you in 12 minutes, more or less. Okay. Are you still here? Please write in the chat if how many of you are still with us. So don't be shy. Please write something. Also, I'm tired is accepted. So at least we know you are here. So okay. I think 10 people brought something, so at least 20% of the participants are with us. Okay. So let's go on with the second part. So we have 1 hour more or less to try to understand what what are these devices and what are the quantum algorithms that work on the devices that we have today, like Pascal device, like also IBM, Google device, so the device that we have today. So, okay, this we have seen this yesterday, 2 days ago. So before this, so the old school quantum algorithms are like Shor algorithm, Grover search, quantum phase estimation, all the algorithms that show some speed up. Usually, they show some speed up like Grover. It's a quadratic speed up, exponential speed up for sure. So with respect to the number of so the number of operation with how the number of operation grow with the size of the input or the size of the of the problem they were trying to solve. There is one question. Does the reliance? Okay, well, actually, the coherence times for this kind of devices are much longer than those that we have for superconducting circuits. Okay. The difference probably is that superconducting circuits, you can apply also gate very fast. So the coherence time is limited. For example, for superconducting circuits, you can have, I'm not sure, but something like coherence time of the order of microseconds, but then the rate at which you can apply gate is maybe 1/10 of a microsecond. Okay, so or even less, probably nanoseconds. I'm not sure, but you can apply a lot of gates in superconducting circuits, Okay, but let me finish. In ion traps or neutral atom traps, you can reach long coherence times. Also, so of the order of seconds. But then the problem is apply gate takes also time. Okay. Actually, persistent stable qubit. I don't see. No, actually, so the coherence time is not a problem for atoms. Okay, they can be. So you can place them in. So the coherence time is not a problem for them. So the problem is basically, yeah, the ratio between coherence time maybe and the time it takes to apply a gate. Okay, if I mean right now it takes time to apply gates on this kind of devices. Okay, so yeah, we yeah, exactly microsecond. Yeah, for superconductive circuits, yeah, microsecond. Yeah. Instead, I think yeah, the record for atoms in superposition was done exactly with I mean was done with atoms, something like ions or neutral atoms. It's of the order of minutes, I think. Okay, but what they did was just put them in superposition, so they didn't do anything. Okay, in quantum computing framework, yeah, this kind of technology, I mean, it's promising because of all the things that we have seen today. Okay, topology, you don't need, you can stay in room temperature, so yeah. But the coherence, so keeping them in pretty good coherence in absolute terms, it's not a problem. Well, so for sure it's not clear right now, but well, uh, so well, I think so for neutral atoms. So first of all, they choose this kind of rubidium atoms because they had so this decay time that is longer, no? Probably with respect to other elements, and that's one thing. I mean, in the future, I don't know. Don't have a clear idea of why. I mean, if they what they're doing, so they're in their people from Pascal have, I mean, expert in manipulating atoms. So people that work with manipulated atoms for decades, if they can say, I mean, we can reach 1,000 qubits in a few years. Then 1,000 qubits is gonna probably is gonna be a lot, and you can do a lot of things with 1,000 qubits, even in this, even if the device is noisy. Okay. So I'm not sure. So for sure, I mean, it's a promising technology. It is still not clear what will happen when we scale up. But scientists that are expert in manipulating atoms like this say that could be possible. Okay. However, and we just need some thousand of qubits probably to have some advantage, okay, using this kind of technology. So let's go on, okay. Okay, we have already seen, okay, this old school quantum algorithm that came up in the 90s, like Shor, Grover, and what happens is that they assume to have ideal ideal qubits, so not subjected to noise or errors. So in order to run this kind of algorithms that have a provable speed up over the classical counterpart, okay, you have to be able to perform error correction. So they need error correcting quantum computers. So some of the things that you have seen yesterday. So you need to somehow to add ancillary qubit in order to be able to measure, to perform the syndrome measurement. So to try understand what error is going on and then correct it. So applying the proper set of gates depending on the outcome of your syndrome measurement. And then what you're doing is, so what you need actually is a large-scale quantum computer because of this redundancy, and because you need many ancillary qubits. And this kind of device is going to be available in 10 to 20 years. Nobody really knows when, okay? But, so right now, so we enter in this era that is called the NISQ era. So this term was introduced by during a conference like in 2018 by right now I don't remember the name, but it's a famous quantum computer scientist. And the meaning of this word is noisy intermediate scale quantum. So let's analyze, okay, every part. So intermediate scale, what does it mean? It means for what concern general purpose quantum computers, so like IBM or Google, we're talking about devices that have 50 up to hundreds and thousands, I mean, up to 1,000 qubits, okay? That's where we are today, okay? Because IBM has 65 qubit machine, Google 53, probably a 70 qubit machine, but not working very well. So we will stay in this intermediate scale era until we reach the situation. We reach the situation where we have devices of the order of thousands of qubits. Okay, 1,000 of qubits, let's say. For what concerns quantum annealers, so there's also intermediate scale because quantum annealing it's easier. Quantum annealing is easier to build than a general purpose quantum computer, so working on gates. And for right now, the most advanced is the wave advantage that has 5,000 qubits. So intermediate scale is going to be thousands of qubits. Okay, so and we're still in the intermediate scale. Okay. Then there is the noisy. So for what noise? Okay, noise. We've seen yesterday the noise mainly due to the environment, for example. So and there is so for general purpose quantum computers, okay, that belong to this NISQ, so to the NISQ type of devices, we don't have enough resources to perform error correction, so which means overriding the number of qubits. So we just try what we can do with without error correcting anything. What does it mean? It means that we cannot run circuits that are too deep, which means that circuits that are that involve a large number of gates. So, for example, like roughly, if the error rate is something like 0.1% for a single gate, then it means that we can run circuits that have at most 100 elementary circuits, okay, elementary gates, okay. These are also called shallow circuits, okay. So limited depth, okay. The other thing is that if you also apply too many gates, you exceed the coherence time, okay. That's also another very important thing, okay. For quantum annealing instead, of course, by default, quantum annealing doesn't need error correction, okay? But however, is still not clear, okay? In quantum annealing, how noise, due to the qubit quality, will affect scalability. So performances when we are try to solve large problems, okay? So far, so the D-Wave went from 2,000 machine to a 5,000 qubit machine, and they were still able to increase the performances. Okay, so the 2,000 qubit was garbage with respect to the 5,000. Okay, so it's much better. Okay, they definitely increase the performances. Okay, but will it be true also going to 5 to 10,000, 20,000? Nobody really knows. Okay, but yeah, the current status is this one. Okay, so as I told you before, what people have tried to develop in the last let's say 3 years are hybrid quantum classical algorithms. So this kind of algorithms have some part that runs on a quantum computer and a part of on the classical computer. So let's say what you do with your quantum computer is you run a circuit, then depending on the output of your quantum algorithm, I mean you send the output of your quantum algorithm to a classical computer that somehow analyzes it and tells, analyzing the output, tell you how to modify the quantum circuit. Okay, how to change your quantum circuit. And this is a loop, so every time there is a change in your quantum circuit, and at the end, after some iteration, you hope to converge to a good solution. Okay, so let's see now. Probably was a question that was asked before. So what are these kind of algorithms? How do they look like? Okay. Yeah. So the quantum part is so you substitute. I mean the quantum part of the algorithm is employs circuits that are called parametric quantum circuits. Okay. So they are circuits, briefly, that let's say that employ gates. They use gates or operations in general, which depend on some parameters. So, for example, here we have gamma 1 up to gamma 6, okay? That could be, for example, arbitrary rotation. So you add some phase or rotation of an angle gamma. So of course, you need to insert both single qubit gates and entangling gates. So like C naught, okay? C naught and then rotation and C naught, for example. So it's gonna look like a real quantum circuit. But this kind of circuit alone, so with random parameters, doesn't do anything in particular, okay? The circuit, again, is not corrected, and it has limited depth, okay, because of the hardware constraint, okay? We know that. You cannot exceed, basically, 1,000 gates, no? Okay, due to errors and credence time, okay? And then we have the measurement part. So this was the quantum algorithm part. Let's see the whole thing together. So what's the working principle of this NISQ algorithm? So at first, you choose the shape of your quantum circuit. So of your, so you decide which gate you want to introduce in your parametric quantum circuit. And this is something that is called a variational ansatz. So ansatz means like the initial choice of your circuit, okay? And this will define your state, the state associated with your qubit, that is going to depend on some parameters, on a set of parameters that are these, in this picture here, are the gammas, okay? And how do you choose your ansatz? Depends on the problem, okay? Could be something that is, the way you choose your gates could be, like, could come, I mean, the way you place your gates could reflect somehow some property of the problem that you want to solve, or could be something that you choose the gates that you can, that your hardware can perform well. So it's like a choice, an ansatz that is hardware efficient, okay? So for example, if my Qiskit doesn't have, so if this qubit is not connected to this qubit, I won't do a control operation that connects this one to the last one, okay? This is the meaning of hardware efficient, okay? Something that your hardware can implement easily. So, and then, of course, the second step is to implement this variational ansatz, this parametric circuit on your quantum computer. Then the third part is the measurement. So when you measure, what you do is you calculate some, you use your measurement in order to calculate some cost function associated to your parametric circuit, so to your parametric quantum state. Then you pass this the cost function to a classical computer that uses optimization technique, which could be gradient based, like gradient descent, or gradient free, like the one shown here, which tell you how to modify the parameter of your parametric quantum circuit. Okay, so it tells you how to modify, yeah, the parameters of your quantum circuit. Okay, then there is, and it is as we have seen, it's a loop. Okay, because once the optimizer tells you what are your new gammas, you implement it again in your QPU, then you measure, and then you optimize again. So the initial choice of the circuit is left unchanged. What you change is the parameters. Okay, and so this is something that is very similar to a heuristic algorithm. Okay, the cost function depends on the task that you're trying to solve. Okay, so what you usually do here is you measure like we did yesterday. Okay, you measure the qubit to be you measure in the Z basis. Okay, you measure 0 or 1s, for example, and depending on your outcome, you compute some cost function that is a function of your output, of your output string. Okay, this is general formula. Okay, depending on the yes, exactly. Okay, the point is exactly that. Yeah. So what you want is to what's the aim of everything is to optimize your circuit. So this is the loop. Okay, you start with random parameters, with random parameters gamma, then you optimize again and again with the aim of finding a circuit, which means a quantum state that solves your problem, or in other terms, that minimizes somehow your cost function. Okay, that is optimal for your cost function. Yes, exactly. Yeah. Okay, the cost function depends on the problem. Okay, for example, for problems related to molecules, is going to be associated to the ground, to the calculator, to the energy of the molecule. If it's a machine learning problem, it's going to be a classification error. Okay, so the cost function is going to be related to the classification. Okay. Oh. So okay, let's go on a little bit. So this is the loop. Okay. So start with random parameters. You classify the parameters with gamma. You update them, and you perform a new quantum iteration, and so on until you reach some convergence. Okay. So this kind of quantum algorithm, the scientific community believes that this NISQ technology with NISQ-ready algorithm could outperform traditional classical computers for specific applications. Okay, outperform doesn't mean like for Grover or Shor, no, to have a speed up. Okay, it's not only that. They could have a speed up. Okay, so you can get the solution faster, or they can maybe not faster, but they can also find better solution. Okay, that are maybe not accessible to classical techniques. That's because when you're doing your circuit, you are employing quantum entanglement. That is something that classically you never have in whatever algorithm you're using classically. No, so the idea is that even though it's not faster, maybe the solution is different or more or better somehow, because you're using something that you're looking at patterns in a purely quantum way. Okay, that's basically the idea. Okay, and what are the applications where this kind of variational and parametric hybrid approach could be used, could be helpful? It's chemistry, optimization, and machine learning. Okay, these three big areas. Okay, so yeah, as we've seen in the beginning of the lecture, so for quantum chemistry there is this does the update of parameter gamma work? Okay, you can work. So I mean, it works in the same way you do it classically. So basically, you have to optimize some function, and you can use these methods that are classical method for optimization. You can use gradient descent or gradient base, for example, Cobila. Okay. Okay. So depending, yeah, on the what's on the time of cost function, somehow it's more convenient to. So, but these are like classical optimization methods. Okay. For basically gradient descent, how it works is given your current state, it calculates the gradient of the cost function and tells you which is the direction in which you have to modify, let's say, your current parameters gamma in order to end up in a solution that is in a lower position by when you look at the cost function, okay, where the gradient is, okay, is like this. Yeah, exactly. The descent, you go. I mean, if the function is as like a single valley, you start from a point that is far from the minimum, and you do the descent. So you go in the direction where the gradient is more negative, like, okay. Yeah, these are classical optimization. Okay, this is all. Once you've done this step, this step, the measurement, then everything is classical. Okay. Yeah, like okay, backpropagation is something that's very it's related to neural networks. So yeah, in backpropagation you can use gradient descent. So, but taking a longer descent can be used also in this case, okay? But also Bayesian optimization, SPSA, there are different, also gradient free, that you do not calculate the gradient, because actually calculating the gradient for quantum in this quantum hybrid quantum world is not easy. So it's better to use probably gradient free methods for optimization, but everything here is classical. Okay. The quantum computer, it's only something that you use. I mean, the working principle of everything is very similar to what people do on neural network. No, you substitute the concept of neural network with a quantum device, okay, which has some structure, okay. So you run your quantum device with some parameters. So it is a function of your parameter, and you see the output, and then you optimize the parameters, okay. Yeah. I mean, what you yes. I mean, you know the cost function, and what you get here is something like an input to your function. Then you can calculate the output. If the output is high, then the optimizer tell you how to modify your input, okay, somehow. Yeah, it's calculated classically. Yeah, you know the function. It's like when you know, it's like the cubo problem that we've seen yesterday. Okay, of course you know the cubo, but then you evaluate like quantumly, okay, on some input. Is it something more or less similar, or yeah? So okay, I was saying, so we have this quantum chemistry, quantum optimization, quantum machine learning that are the techniques. I mean the areas where this NISQ algorithm could work, and we have three different algorithms. So we have variational quantum eigensolver, QAOA, which is quantum approximate optimization algorithm, and quantum neural networks. Now let's see how it works. Okay. So yeah, okay. What's the difference, first of all, between them? The difference. So the working principle is the same. The main difference between these three methods is, okay, of course, in the problem that you want to address, but also, which means the difference mainly is in the quantum part, so in the variational answer. So in how you choose your parametric quantum circuit, okay? Because as I told you before, the parametric quantum circuit may reflect, okay, some properties of the problem, okay, that you want to address. So that's why the main difference is in this part here, okay. Then the rest is more or less the same, okay, because you have classical optimization, okay. So the main difference is in the choice of the gate that constitutes your parametric circuit. Okay, let's now talk very briefly about variational quantum eigensolver. So it's used for quantum chemistry. Here you see a paper, this paper here, there is the link from IBM, where they used something like 7 qubits probably to and this VQE, variational quantum eigensolver algorithm, to calculate the ground state of different small molecules, right? Like H2, lithium hydride, and beryllium hydride, I think is this one. So there are small molecules, but they prove, okay, the principle, the principle, in principle, that it could work, okay? So in VQE, again, the objective is to calculate the ground state of molecules with, okay, the idea is if you have a powerful enough quantum computer, we will be able to go beyond the mean field approximation, that is something that is nowadays used in quantum chemistry, but which is also classically so an approximation that is actually, however, classically very expensive in terms of resources. So you know that in order to simulate exactly nature, no, you need an exponential number of resources. So this goes a little bit in the direction of the original idea of Feynman. So in order to simulate something that is quantum, you need a quantum simulator. Okay, so this way, yeah, variational quantum eigensolver goes exactly in this direction. No? So then, as I told you, for what concern this method, you can have a different parametric circuit. No? You can choose. You have to choose an ansatz, which means an initial guess of the ground state. Okay, so the ansatz could be chemically inspired, for example, and there is a method for building your parametric circuit in such that your variational ansatz is inspired by the chemical the atom, for example, that you want to study. Next technique is called UCC, which stands for unitary couplet cluster, or like in this paper here by IBM, what they implemented is an hardware efficient ansatz, which means which is the one shown here. So basically, each qubit represents something like a different orbital of the molecule, and then you have multiple layers. So you have rotating rotating gates, so single qubit rotating gates, and entangling gates, and then in this layer here is repeated d times, so many times, and then they perform the last operation and the measurement, okay, with the aim of getting closer and closer to the correct ground state of the problem for the molecule, okay. So as I told you, the ansatz in this case gives you a guess, no? A guess, a provisional molecular ground state, no? That you then optimize with the classical optimizer, and that let's say evaluate the solution, the current solution, depending on the energy, and then with the gradient or gradient-free method tells you how to modify in a smart way the parameters in order to get a better approximation to the ground state. Okay. This method, okay, what's it's PQE, or the promise of studying, okay, large molecules. Okay, once we have quantum computer which is bigger, no? Probably with 100 qubits, you can do already something that is not study just the beryllium hydride, but something that some molecule that start to be hard also for supercomputing systems. Okay, so this method holds the promise to study large molecules with an accuracy that has never been reached. Okay, once you have a NISQ computer, quantum computer, but still of the order of some 100 to 100 qubits. Okay, 150. Okay, so yeah, that's it for BQE. But then we will have also Professor Leonardo Guidoni that we talk more in detail about BQE. QAUA, which are optimization problems. So solve optimization problem like, you know, routing, scheduling, portfolio optimization. So you have optimization problem in every aspect of in different in multiple real world scenarios. You always have some kind of optimization problem. And QAUA, which stands for quantum approximate optimization algorithm, try to solve this kind of problems. Okay. In QAUA, okay, the objective is solve some combinatorial optimization problem, like in quantum annealing, for example. Oh, here the ansatz is done in the way shown on the right. Okay, so it's an alternation. So a repeated alternation of two circuits. One is UC and one is UB. Okay, you can also see it here. Okay, so the initial state S is the one where you have all the Hadamard gates, so that that's why you have all the plus here. And these two circuits are parameterized by some number gamma and beta, respectively. Okay, so at first, okay, maybe in this picture it's clear. Okay, first you have the UC circuit, UC set of gates, and then you have the UB set of gates. The first one is parameterized by gamma 1, the second one by beta 1, and then you repeat this multiple times, and you get every time a different variational parameter. Okay, then what happened? Why do this problem solve an optimization problem? So in a way that is similar to quantum annealing, you have these two terms. Okay, the first term here, the UC term, encodes somehow the problem, the optimization problem that you're trying to solve, which must be in the form like a cube or Ising problem, okay? And B is the one responsible for the searching, no, in the configuration space using entanglement. So yeah, exactly. We have seen here, okay, this is initial state where everything is on superposition, is a plus, and then you alternate this circuit UC, UB with different parameters, and then you get a solution. Again, as we've seen before, you calculate some, you measure, you obtain some input, and you evaluate your cost function, and then you optimize classically the variational parameters, okay? So here, what is UC? UC is something that looks like this. So it's the evolution. So it's a unitary where C basically, or HC is, for example, C could be your, as I told you, your Ising problem, no? Associated with some graph isomorphism, I don't know, some problem that you formulate into as an Ising problem, or some Hamiltonian, okay? Then the B term basically is a collection of x's, okay, of it's something that looks like this. So it's like a sigma x is a bit flip, but you have the beta that defines your phase, okay? So this beta parameter, okay? What's how do you know the conversion? Yes, exactly. So it's like in classical cases. So well, actually, okay, for QA/UA, for QA/UA, there is the result that tells you if you apply, so in the limit where you apply an infinite number of layers, of these layers, you get, so in the limit where the number of layers goes to infinity, you exactly get the optimal, okay? But of course, you cannot place an infinite number of layers, so you are not guaranteed to have the convergence to the optimal, but the more layers you introduce, the better, okay? So this thing, for the others, yeah, it's, there's no guarantee for any kind of convergence towards the global optimum. So yeah, it's like in a classical case, okay? Okay. Then we will see also an example of QA/UA, where we see that, okay, if your problem is easy, you maybe just need one repetition, okay? Then when the problem gets harder, you need more and more repetitions of P, okay? But you, in principle, don't know how many P is enough for your problem. In theory, if you put enough of them, you get arbitrarily close to the optimal, but okay, it also depends on the hardware, okay? You cannot put thousands of these layers, because then you get outside of the possibility of the quantum hardware, okay? So basically, you try, okay, with the number of layers that you're confident your machine can handle, okay? This is a more practical thing, okay? Yes, okay, as I told you, this part here encodes the optimization problem. So for example, C could be some Cubo problem, while this other part is the exploration part. It's something similar to, so this term is like the final Hamiltonian in quantum annealing, and this term is like to the initial Hamiltonian in quantum annealing that drives everything, which is responsible for quantum tunneling, no? That tries to explore the solution space. Okay, it's the idea behind it's basically the same. Okay, and you alternate these exploration steps. Okay. Also here, okay, the challenge, okay, is to find probably a class of problem for which QAUA is better than the best classical algorithm. Okay, this is still okay, something that is going on in the research. Okay, and yeah, for optimization problem like quantum annealing. Okay. Finally, we have quantum neural networks. So what is briefly neural network? Okay, probably most of you know this. So in supervised learning, we know that the algorithm is asked to reproduce the relation between inputs and outputs, and the neural network is a supervised learning algorithm that is able to classify, if properly trained. So you have to train these parameters, and you evaluate some cost function, and then you update the parameters. So it's very similar, the concept to NISQ algorithm. And if properly trained, the neural network then is able to classify new data, even those that the network has never seen. So one easy example is to classify, animals. So it's to classify dogs and cats. So the neural network is something that has different input as an input layer where you encode some of the picture or the input data set, so the vector, the input vector that you want to classify, and it has different neurons or that compose different hidden layers. Then the output is going to be like in this case either cat or dog. Okay, and here you see it says cat, and it is correct. The idea in a quantum neural network is very similar. So, I mean, it's similar, but could be also different. Okay. So the goal again is the same. So you have to classify something. Okay, you have a supervised machine learning problem. Okay. Usually the ansatz consists of a feature map, which is so a set of gates that maps your classical vector, that could be so the photo of a cat, into a quantum state. Okay. So, and it has to do this in a way that uses entanglement. So you want entanglement to enter in this part. So basically, what you're doing is you are mapping your vector, your classical vector, into the Hilbert space of quantum states. Okay, this is a much larger Hilbert space. Okay, where then you train with the variational part the neural network to classify. Okay, feature map serve. The feature map is responsible for mapping everything into a quantum into the state of a quantum into the quantum Hilbert space. Probably it's something that is larger than the input space. Okay, because for example, if you use x an input x with n, so if your input x has n elements, so for example, okay, if the picture of your cat has I don't know 20 features, so as 20 elements, the vector that represent your cat, then gets mapped into something that is like the state of 20 qubits. whose dimension is 2 to the 20. Okay, larger than the input space, the classical space. Okay. Yeah. Okay. Okay. Yeah. Sure. Yeah. If you're talking about pixel, it means that you need I don't know how many pixels. If you need 500 pixels, then you're gonna need. I mean, you try to do something. Probably you don't have to have 500 qubits, or maybe you can use less qubits and the same qubit to encode the same. Okay, it's not here. Is not always this. So you don't. So I mean, you want to use. So in some proposals, so this is very recent, okay, stuff. So this paper here is called "The Power of Quantum Neural Network." Is from the this paper is from the December 2020, you know, where the IBM shows some what could be the power of quantum neural network. Okay, so it's more the idea of what you have in support vector machine, where you map the dimension of the problem into a higher dimensional problem. So the starting point is always to use the fact that with n qubit you have 2 to the a space of dimension 2 to the n, so to increase somehow the dimensionality. So to use that feature that is this feature of quantum system that classical you never have. So with few resources you get a space that is exponentially bigger. Yes, for image, the input size should be much larger than maybe, but maybe still smaller than. I mean, the feature map. Okay? Let's see. So the idea is to train the circuit. Okay, this variational part after the encoding. And the variational part has to recognize, okay, has to solve your problem. Okay, let me show you some possibilities. Okay, so this is the research going on in quantum neural network, quantum machine learning is very hot. Okay, so one question is exactly that. So is what is the smartest way to encode your dataset into the state of quantum bits, into a quantum state? Okay, so nobody knows exactly what is the best way. People right now have tried what I told you. So they use 1 qubit for every feature that you have. So for every element of your vector, which means if your vector is 10, you have 10 qubits. But for example, like in images, if you have a vector that is an image of 500 pixel, then you don't have right now a quantum computer with 500 qubits. So you have to be smart, and you have to group together sets of. So for example, the first qubit encodes the first 10 element of your vector with different rotations. Okay, so there is a recent paper by Google that does this on. Maybe I can send you the link in the chat. So now I'm gonna find the paper. Okay, and this is very fresh. It's 2021, January 2021. Okay, I'm gonna send you this paper. What they do here is they use something that is they focus here in the encoding. So there is no variational part, but they show you how to, is it possible to encode in some smart way. This is one paper. A data set that is high dimensional into a quantum state, and which works pretty well. So, but in general, you can have different kind of neural network. Some of them may have not only different variational layers, but also multiple re-uploading of the initial data set. Or here, like in convolutional layers, you encode your data set, but then maybe it's related to what you were asking. You reduce the dimensionality. So at first you increase the dimensionality because you encode everything into a quantum Hilbert space. But then you reduce the dimensionality via measurements. Okay, so there is these pooling layers where you classically you reduce the dimensionality. Here you reduce it via measurement. So measurement that then conditional measurement. So measurement and then whose result modify, okay, the gate here, no? And it's an alternation of this pooling layer where the dimensionality of the quantum Hilbert space is contracted via the measurement, okay? Then, or you can also have dissipative quantum neural network. That is something completely different from what you have classically, where you perform something like this, and on n cube on several qubits, but then you after some steps you discard some of them, and at the end you look at only at the output on the last n register. Okay, so the possible choices here in quantum neural network are so different, and there is much more variety, I think, with respect to classical neural network, and that's where the research, a lot of research is going on in this topic. Okay, that's why. So I think we can stop here because it's almost time for the presentation by Leonardo Guidoni. Daniele, are you here? Or
Yes, I am.
Okay. Do you know if Leonardo is here with us?
Yes, Leonardo is here with us, or at least his name is on the list of our hosts. And here it is.
Okay.
Hi, Leonardo.
Hi.
So,
Hi.
good morning, everyone. Leonardo is a friend of us, and he is a full professor at the University of L'Aquila as a professor of chemistry, working on the physical and chemical science department. And today he's here for a lecture on variational quantum eigensolvers. So thank you, Leonardo. Really appreciated your presence here. And the floor is yours.
Thank you very much for the presentation. Okay, I can share. So it's not clear to me which is how heterogeneous is the audience. So
really much, Leonardo. Really much. We have a lot of people. We have 51 participants, and they are ranging from students to professors. So
okay, but what
really
is the background? Mainly physics or not?
Mainly physics, yes. I think mainly physics, but of course you can talk about chemistry as well, and there is no problem. Think about a PhD audience.
Okay.
Yes, some of them computer science, some physics, some machine learning, maybe some.
I think we have everything.
Chemistry, yeah.
Okay,
more or less.
Name one.
We cover all the.
That's very good. Okay, just to know what are the knowledge of the audience. Okay, I can share directly my screen.
You should be.
Yes, I can do it, and that's it.
Okay.
Okay, so So I would like just to have a short introduction to how to calculate, how to use quantum computers to calculate quantum chemistry problems. Okay, so the idea would be, the goal would be actually to, it's in some way summarized in this picture. So you have a quantum computer here, you have a circuit, and then you would like to model very complex chemical systems like the one that is shown in the pictures. Unfortunately, the state of the art is not so exciting, because up to now we can model very simple molecules, and actually we cannot really yet go beyond classical computers, this for sure. But we are confident that due to the development of NISQ devices, we can arrive very soon to build some quantum chemistry calculation, which is actually useful. So why quantum chemistry? Quantum chemistry is on the floor because algorithms in quantum chemistry are quite robust against noise. I mean, they are more robust against noise than traditional algorithms. This, I think that you have already realized that as soon as you have to use, for instance, a coherence or maybe in other way interference to exploit your quantum computer through some kind of algorithm, then the noisy device have a a lot of problems. So in some way, quantum chemistry, especially in using this variational quantum eigensolver algorithm, are suitable for this purpose because they are quite robust to noise. So what is the problem we want to tackle? The problem we want to tackle is we start from the molecular Hamiltonian. What is the molecular Hamiltonian? It's a kind of it's a functional of positions and momenta of electrons, which are around. Which are moving in a field which is given by the nuclei. This just to be very general, and this is very important to understand how electrons behaves, because all molecular properties can be derived if you exactly know what is the state of your molecule. Molecular property means how these molecules interact with light, and what is the energy, and what actually can understand by a computer simulation of the protein. This, of course, is important in many fields, in chemistry, in pharmaceutics, and in material science, and so on. Okay, so that will be a bit hard, maybe this part, for people who are not in physics or chemistry. Electrons are to be turn out to be fermions, and fermions needs a fully antisymmetric wave function. So usually fully antisymmetric wave function is described by a Slater determinant, because determinants are fully antisymmetric objects. But it's very convenient to go beyond this description and use what is called the second quantization. Second quantization allows the description of the state. So in this slide, n is the number of the electron. So there are n electrons. And each electron is described by an orbital which might think to be for instance, the atomic orbitals, which describe the state of a single atom. The second quantization has the advantage, which is very, very compact, as you can see here, and you can forget in some way about the antisymmetric properties, which is enforced by Slater determinants, because you can define your state as the creation of your particles on a reference state, and these operators that create particles and then annihilate particles are such that they can take care about the antisymmetric properties of your wave function. So this might be a bit obscure for people who are not in physics. For the other people, I suggest to think that anyway we are dealing with the kind of cost function. Okay, we are dealing a kind of a cost function, and this cost function is function of a set of discrete variables. Basically, you go from the Hamiltonian written like that in this scheme to an Hamiltonian written like that. An Hamiltonian written like that is the second quantization Hamiltonian, which is described in terms of this creation operator. Each of these operator, so the DAG operator, can create an electron on an orbital p, and of course this destroy an electron on an orbital q. So there is a complete equivalence between the electronic Hamiltonian and this formula, but this formula is more compact and can be seen as I said before, as a kind of cost function, just for people who are not in this field. Okay, now we have to go from the space of electrons to the space of qubits, and this can be done in different way. The simplest way is the so-called Jordan-Wigner mapping. What is the Jordan-Wigner mapping? Basically, what you are so you can describe your state as a sum of determinants, and this sum of determinants is actually translated in a sum of orbital occupations. So when you have a determinant which is formed by the first, I don't know, 10 orbitals, then this mapping will set a value of 1 in the first 10 qubit and value of 0 in the other qubit. So basically you can transform the problem, and now it's much easier to understand for everyone, in a kind of cost function like that. So the Hamiltonian, mainly, so you can think as the cost function, is actually reduced to a sum of Pauli matrices with different coefficients. Okay, so we have a Hamiltonian which is living on 4 qubits, because there are 4 length 4 Pauli strings, and with several coefficients. And so this Hamiltonian is the Hamiltonian that we want to study, and is in some way the cost function that we can we want to minimize. So as we say, 1 and 0 are occupation number for electrons. So with the same with our wave function written on the qubit in the qubit way, we can describe a superposition of determinants. That means we can describe a superposition of occupation of orbitals, and which in principle we can describe also the solution of our problem. Okay, so then we have to look a solution. The solution is using the variational principle. We know that if you have an arbitrary wave function, then its expectation value on the Hamiltonian, that means on the cost function, is always larger than the lowest eigenvalue of this Hamiltonian. And what we would like to find is actually this lowest energy eigenvalue. And in order to achieve this goal, we can search in the space, in the variational space of our wave function. What this means? It means that you can build a circuit which depends on how many, many parameters. You build a circuit that depends on many parameters, so these theta parameters. Then you can evaluate in some way this expectation value, and then use a classical optimizer to optimize the theta parameter in order to get the lowest possible expectation value. So this is the way is working the variational quantum eigensolver, which is, as you can understand, is a hybrid quantum classical algorithm. So quantum computer is used to describe and to prepare the state, so state preparation. And then it's also used to evaluate this expectation value. This expectation value can be evaluated because your Hamiltonian is a sum of Pauli strings, so it's actually simply a measure of Pauli strings, maybe many Pauli strings, but you can measure them. You can measure through several measurements in order to have an estimation, of course, of the average of your Hamiltonian on your circuit. Then the classical computer is used to process the measurements and try to update the parameters of your circuit in order to go lower in energy. At the end, you will end up with an optimized wave function, which is which reach the lowest possible energy. Of course, this depends on the ansatz. That means on the wave function you would like to on the variational complexity of the wave function that you would like to design on your quantum computers. So variational quantum eigensolver, which is also applied to other fields, it's powerful, but what is really crucial is how to parameterize your wave function. So how to write this theta and how to write the circuit, and this is the main research, I would say, in quantum chemistry. Okay, so this is just another summary. So you go from the molecule to the mapping, the qubit Hamiltonian, which is just a sum of Pauli strings. And then the algorithm works that you have to prepare a trial state and measure expectation values on a quantum computer. This is an example of other mapping. So in the mapping, John Amiga mapping, you have a mapping where the 1 and 0 represent the occupation of the orbitals, but you can, in principle, use other mapping in order to create your own Hamiltonian, qubit Hamiltonian. Okay, what about the state preparation? For the state preparation, there are several strategies. Maybe I will show you later this. This is a general scheme that we have already seen in some way. So you prepare the state, you measure the expectation value, and then you optimize. Because you calculate the energy, you adjust parameter, you optimize up till you arrive a solution. The solution, of course, is a variational solution, so it's not the true solution, but it's the best solution that you can obtain given the answers. The answers, right? This is an example of optimization. You have energy, and then as the algorithm is proceeding, you can optimize, you can jump a bit, but at the end you arrive to a certain value, which is the best value you can get for this answer. For this, sorry, I have to switch presentation. I tried to mix this morning, but it seems it was quite challenging for PowerPoint. I don't know why. Okay, so about the answers. So how to take the answers? The answers, you have two choices. You have to choose. One choice is to be inspired by some physics, by some chemistry. So bring the circuit by inspiration of traditional methods, classical methods. Or another way is to just take the circuits in order to be optimal for the real hardware. So I don't care about the meaning of the circuits. I just want to be circuits which are efficient on that hardware. This is just an example of measurement. So this is your energy Hamiltonian, okay, which is sum of several strings. And then you have to measure basically each one of the string independently. So if you want to measure the x, z, x, so this is an example of measurement of particular Pauli string. Of course, you have to repeat these measurements for many times. And then in this way, you can evaluate the average of h. Okay, one example of a quantum chemistry inspired wave function is represented by unitary Kappa cluster. I don't want to enter in the detail of this wave function, but just to say that you can have sometimes the perfect translation on your circuit of some classical theory. So this is, for instance, one example of how the circuit translates in a very simple way. So this is the UCCSD operator for H2 in a minimal basis. So you have some classical operator. What is the problem of this kind of approach? The problem of this kind of approach is that it's quite bad scaling for the number of gates. So you have very bad scaling for the number of gates. So if you use quantum chemistry inspired ansatz, you have actually very long circuit. And very long circuit, as you know, it's not the best you might hope on NISQ devices. On the other hand, you have complete control of the circuit because it's you know the accuracy because it's something that you have already used, for instance, for classical quantum chemistry. But really, this kind of circuit cannot be used in practice with current devices. So another way is to just use this, just be inspired by the hardware. I mean, the hardware is, for instance, it's not bad having CNOS that can be, I mean, compressed in some way in time, and so the most compact, and then you can apply a qubit, 1 qubit operator all at the same time without much problems. So in some way, one hardware-inspired ansatz that has been proposed for variational quantum eigensolver is this one, that where you have basically a repetition of rotations that can be whatever rotation, and entangling blocks. So you have a block which has rotation and entanglement, which is repeated many times. But of course, the parameters of these rotations are the variational parameters, whereas the entangling, the way you have the entangled in one block or in the other can be the same or can be different. But at least you have something which is very compact. That means you hope not to lose your coherence by very long circuits. So this is very good because it's compact, but it's very bad because you lose all the chemical meaning. So there is quite an interesting new field now in quantum chemistry, because you would like to recover in some way the physics and to understand how these new hardware efficient ansatz can be interpreted also from the chemical and physical point of view. Okay, now I want just to show you one further step, which is very recent work that we have done in collaboration also with IBM Zurich, and it's an extension of variational quantum eigensolver. When you would like to extend your wave function to a non-unitary wave function. The advantage of having non-unitary wave function, of course, wave function, all wave function that you want to, that means ansatz that you have to write on a quantum circuit, of course, has to be unitary. But in this way, you can extend the description of the unitary wave function also to include non-unitary wave function. And this has the advantage that you can use non-unitary operator in front of that. Of course, then the wave function has to be normalized later, because if it's not unitary, then you have to. Maybe we can.
Sorry. Oh, okay.
Thank you.
No. Sorry, there's someone with the mic open. I cannot see who is. Seems there is some problem because seems to be
Too many people. Maybe now I switch it off.
Seems to be an error because it seems to be an user, but I'm trying to deactivate his audio, his mic, but I cannot. Maybe now.
Anyway, I don't hear
Okay.
him anymore.
Okay. Sorry for the interruption.
So this was a work where we tried to extend the use of ansatz to non-unitary. Actually, would be interested to know also the opinion of other people, whether this approach can be applied to other fields, not only on quantum chemistry. So you describe your wave function in this way. So a part which is a non-unitary operator, which cannot be applied inside the circuits, but has to be applied in some way outside the circuits, of course. And then you have this unitary wave function, which is, of course, represented by your quantum circuit. So when you want to estimate the average of the Hamiltonian of this non-unitary wave function, that is this psi j, then of course you have to evaluate in this way, and you have to normalize the wave function, which is not normalized now. So what we have done is why we were interested in non-unitary operator, because there are operators, similar operators in other fields of condensed matter theory, which are quite useful to describe electron correlation. So we were thinking that using a non-unitary operator to in some way filter out wrong configuration from your quantum circuit, it might be useful. What I do mean is that when so this is maybe an interesting general concept. When you are doing this variational optimization, the problem it is not only to get the configuration which are important, relevant for your energy, but also to avoid including configuration which are not important. And of course, the superposition which is inside your wave function, the way how these two good and bad configuration are linked together is quite intricate because it depends on the ansatz. And it's very difficult usually having an ansatz which has enough flexibility to only to allow the increasing of the weight of the good configuration without also allowing the increasing of the weight of the bad configuration. So in some way, this unitary operator we have used to filter out this bad configuration in some way outside from the circuit. So this is the operator that we have used, but actually we have used also other operators. So filtering is our inspiration. Actually, this J operator it's an exponential, so that means that it filters everything where the argument of the exponential is large, or it's a negative exponential. And then actually we have to linearize this operator, otherwise it's not convenient from the computational point of view. And so this is the linearization of this operator. So basically we have other additional parameters, which are these alphas and these lambdas, and we can evaluate so we don't need only to evaluate Pauli strings of our Hamiltonians, but in addition we have to evaluate Pauli strings also of our Hamiltonian, which has also this operator here. These are quite simple because they are Z, so it's not very bad in computation. So we add more Pauli strings, but they are in some way diagonal. And so we have to evaluate this expectation value. And then, of course, we optimize all the parameters that now we have two parameters, one inside the circuits, which are the theta, and the other, which are the lambda and the alphas, which are outside the circuits. Okay, so this is an example. Okay, how now from here you cannot distinguish the quality of this wave function, of course, because they are all looks quite the same. Here you can distinguish the quality, so you can see that we without the Jastrow operator, we call this non-unitary operator Jastrow operator. You can obtain this purple curve, and with this variational Jastrow operator, we can actually have something which is basically the exact solution for this H2 small example. This is a very important plot because what is important is not only the quality, but is the fact that we can reach this quality with a small number of gates. So basically, this is as a function of the number of blocks, how is the quality of our wave function. And you can see that the fact of adding additional variation variational parameter outside the circuits can lower a lot the depth of the circuits. So basically, we have more than 1 order of magnitudes of gain if we use this non-unitary approach. So this, and also what is important is that this improvement grows with the number of entangling blocks. So it's not something that is stopped, but as soon as we have more possibility to have longer circuit, we always have this at least factor of 10, if not more, of advantage. This is a plot that summarizes the previous data with plotting them as a function of the number of parameters. So this can show that, of course, you have more parameters with our approach, but if you are limited to the number of blocks, and actually you are limited to the number of blocks because noise NISQ devices are limited by a number of blocks, basically, so the circuit length is limited, then you always have an advantage, even if you have more parameters, but anyway, this is always an advantage. Okay, this is also showing that our system, our scheme is working also for the different mapping. So I hope I gave you kind of flavor of how to apply quantum chemistry and also kind of a hint on how to use non-unitary wave function for variational quantum Eigen solver. This is an optimistic, I don't know, plot that I found on the quantum computing report web page that I liked. So we are about here. And these are the different field, quantum chemistry, machine learning, and encryption. And these are in some way different curves that depends on how many logical qubits, how many physical qubits you want to build, starting from logic, how many logical qubits, how many physical qubits you want to build for a logical qubit. And this is, I think, it's assumed just on a Moore-like behavior of quantum computing hardware development. So I think this is something that can show you two things, that quantum chemistry is one of the really next application for quantum computing, and also that we are not so far away. So even if you, I mean, in few years, I think we can reach something that can bring quantum computing useful, not only a test case for quantum chemistry. Okay, so I want just to also talk shortly about this network. You will hear about this network later because it just started. This is an innovative training network, and it's the first network for molecular quantum simulations. So we are inside, but also Cineca is inside. So there will be more activities in the network, mainly developed, mainly aimed to provide a PhD school for in this field. So it's the official kickoff. It's in September, and we will start with a series of events, conference, and workshop on this topic. So the topic of materials chemistry on quantum computing. Okay, so thank you very much. This is the group, and there are the people. In red are the people who are working actually on quantum computation. So I will be glad if someone has some question or curiosity.
Thank you, Leonardo. We actually have some question here in chat. We can start. Cedric was asking, do you work with atomic or with molecular orbitals in complex realistic chemical systems?
Okay, we work with molecular orbital because this is a good starting point. But we are actually working now to modifying orbitals according to variational energy. This is the forthcoming work.
Okay. The other question is from Lucius. He's saying, regarding the mapping from Hamiltonian to Pauli matrices, how would you do in these cases, in cases where a state can have a Capetian number greater than 1? When you're working with bosons, for example?
Okay, we are not working with bosons for molecules, so there are other Hamiltonians that can be another mapping, of course, but it's something that is going beyond this the application of to molecular chemistry.
Okay, very good. You're also saying, would you need multiple qubits to represent a sort of quantum integer? In what sense? I think yes. Okay. So, this is not a question. So, with regards to quantum chemistry, I thought the main motivation for the BOA was to make the problem of solving the Schrödinger equation with the full molecular Hamiltonian with numerical tractable, more numerical tractable. Why still work in this framework then, given that we are not far away from being able to exploit the power of quantum computers? Why not solve the full Schrödinger equation?
Okay, so I don't understand.
The Oppenheimer approximation. If you want to, you have the access to the chat, right, Leonardo?
Yes. Sorry.
You can read it. Maybe I read it badly.
No. I think it's okay, but.
It's the last question, this one.
I don't understand very well, but maybe the I mean, this is just one approach. It's not what I explain today is one approach how to use quantum computing and quantum chemistry. But you can use quantum computing and quantum chemistry also for other purposes. For instance, to have time evolution of your wave function, which is completely different problem. And it's actually very interesting because you have access to excited states and also to true electron dynamics. So even so I don't know if this is answering. So this is just one case how to approach Born-Oppenheimer approximation to solve variationally the Schrödinger equation, but there are many others that can be actually exploited in quantum computation. I think this is maybe one of the more suitable for NISQ devices, but because of the quadrarados.
Good. Perfect. Is there any other question? If not, we can thank Leonardo Guidoni for this interesting lecture. Thank you very much. Also for the reference to MOX. Thanks a lot. And okay, I say that we